Hello, Puppet. How are you today? I'm practicing my English accent because I am fluent in it, so I have to keep it practiced. Okay. All right. So let's see. Today we start acid-base chemistry. Awesome, awesome, awesome. And in fact, if you and I were meeting together, 3 times that we would meet, a total of 15 hours would be on acid-base chemistry and the labs that go along with it. So this is a lot here. This is the big portion of the second unit or second phase of our course in Chem 2. So we have lots and lots of acid-base chemistry, and I want to get started right away. So what is an acid? You've heard of, what's an acid? What's a base? Okay, well, there are different definitions. Yes, there are. I know, it can't be that simple, right? It can't be, this is an acid, this is a base. Nope. Depends who you talk to. It does. If you get your sheet, your list of stuff right here, you will see at the top it says Arrhenius acids and bases, and then it says Bronsted acids and bases, and it's got some little stars around the Bronsted, meaning that's really important. We're going to focus a lot on that one. But the Arrhenius acid base, the definition is also very important. So let's go over that because we will be using this definition, and then actually some of these definitions overlap each other. Yeah, you can have one definition of an acid and it works for a particular acid with 2 different definitions. So there is an overlap in these definitions at some point, but there are differences. We need to know the difference between the 2. All right, so let's dive in. Arrhenius, this is your traditional acid and base. Your traditional acid and base is an acid, has hydrogen. If you got some H, you're an acid. Base, you have OH, hydroxide. All right, so if you have hydroxide, according to the traditional or the Arrhenius definition, you are a base. As a matter of fact, you have to have hydroxide to be a base, and you have to have hydrogen to be an acid. All right, with me? Okay. Example, you've got HCl. All right, your hydrochloric acid, one of your strong acids that we do need to know. And here is a base. Typical base would be sodium hydroxide. That is a strong base. There are weak acids and weak bases as well. As a matter of fact, most acids are weak acids. All right, a little interesting fun fact about this. Look at that. Take these 2 and combine them. What do you get? Lab partner? You see it. Come on, come on. You get HOH. Okay, all right. Okay, you get HOH, right? And what is that? It's water. It's dihydrogen monoxide. You know, that nasty stuff that they tell you not to drink. Don't drink it. Dihydrogen monoxide is poison. Water. All right, so HOH is water. And so what does that mean? Think about it. Come on, think. If you have hydrogen, you're an acid. If you have OH, you're a base. What is water? Both. Boom. Actually, water is what's called amphoteric. Amphoteric. Should I write that down for you? All right. Amphoteric. Can be both an acid and a base. All right, when you have your acid and your base definers, your hydrogen and your hydroxide in equal concentration, you have neutrality. All right, neutral, that would be a neutral, so water. You know, typical plain water is neutral, is a pH of 7. Ooh, yeah, come on, you know something about pH. I'll go over it in more detail soon. But that is our, just toss the mark. I'll be right back, lab partner. Oh. Okay, I'm back, lab partner. I know we're not doing a lab, but you're still my lab partner, and you're my best lab partner. All right, you're my favorite lab partner ever. I wouldn't lie to you. That's the truth. I wouldn't lie. Besides, I'm standing. I'm not lying. I'm standing. I'm not lying. Okay. All right. So there is your traditional definition of acid and base: hydrogen, hydroxide. Okay. Well, what's another one? Well, the one with the Bronsted. If you look at Bronsted, it's got, I put these little stars next to it because it's really important. We're going to spend some time going over a Bronsted acid and a Bronsted base. So a Bronsted acid is, okay, well, let's see, Bronsted acid, it releases a proton. It's a proton donor. It donates a proton. Essentially, a proton is a hydrogen. H positive ion. That's a proton. That's all it is. So what's this saying? Essentially that a Bronsted acid has to donate a hydrogen. Wait a minute. Wasn't that the definition, the traditional Arrhenius definition? Yes. See? There's some overlap I was talking about. Okay. But the base part's different. The base has to be a proton acceptor. It's got to accept that proton. So a base accepts the hydrogen. Now, could that be an OH? Sure, it could be. It could. If I had an OH here, and here comes the hydrogen, thank you, parks itself right there, that hydroxide would be a base because it accepted the hydrogen. So there is a little bit of overlap there when it comes to it can be an OH that is a base that accepts the hydrogen. It doesn't have to be. So there's the difference. The Bronsted is a little more broad in terms of its bases or what can be a base. So when it comes to the acid, the Bronsted and the Arrhenius definition, same. When it comes to the base, they could be the same if hydroxide is involved, but hydroxide is not always involved. Give me an example. Give me an example. All right, calm down. I know you're so excited. All right, so here is an example of a Bronsted base that would not be an Arrhenius base. This is NH3, ammonia. You know what you get when you get sick. You catch ammonia. Oh, I have to correct myself up sometimes. All right, so no, that's pneumonia. This is ammonia. Now, ammonia is a very, very important industrial base. It is hugely important in production of fertilizer and all kinds of things in industry. So it's a very important base. It also happens to be a weak base, and we'll talk about that a little later, but it's a base. Now, why is it a base? Let's draw the Lewis structure for it. Come on, you remember Lewis structures and how much fun they were. All right, we got a nitrogen. It has 5 electrons, 5 valence electrons. It forms 3 bonds with hydrogen here. I'm running out of room here. So we got a hydrogen here and a hydrogen here, and then it has 2 unshared pairs of electrons. And for multiple reasons, those unshared paired electrons are actually very important. I'm not going to go back through Chem 1, but they're very important. They form that's what makes a polar molecule, and it also forms a spot here. For accepting a hydrogen. So if I'm a hydrogen, and I'm just floating around, just doing what hydrogen ions do, just kind of hanging, just chilling, whatever. And I'm going, I wish somebody could take me in. I don't want to sleep outside tonight. Please, please, somebody. Oh, over here, come over here. I got some space right here. Yeah, right here, see? I got space. And you can join, catch on right here, and it'll be sweet. Really? Really? Okay. And so the hydrogen can take this spot. Now the hydrogen, remember, is a hydrogen ion. It's a proton, so it doesn't have any electrons. So that means it could take these 2 electrons, form a bond, and form a covalent bond between the hydrogen and nitrogen, sharing those 2 electrons. So the hydrogen will come in here and go ka-ching, boom, and form with that, taking my ammonia and making ammonium, one of those polyatomic ions that we should know. Yes, we should. That's ammonium. And now, since we added an extra H with the positive, that's why ammonium is I'm doing some review here for basic chemistry 1, but okay, I'll move on. We'll move on. Let's get back to the basicity. I made that word up. Basicity of this ammonia. Why? It accepted the hydrogen. It said, come to me, I'll accept you. And hydrogen went, okay. And latched on. So it accepted the hydrogen base. Okay? We'll have many examples of things that can accept the hydrogen that are not OH. Now, OH can accept the hydrogen, so by the Bronsted definition, OH is a base, just like it is with the traditional Arrhenius definition. So OH is a base because it can accept a hydrogen. Not everything that accepts a hydrogen is OH. There are many things, and we'll soon find out, many things that can accept those hydrogens that are not OHs. Okay, so that is the Bronsted definition. There is the Lewis definition. That's the third one. Lewis, same guy who just did the Lewis structure I was drawing. He did lots of stuff in chemistry. And there's a Lewis definition. We'll get into the Lewis definition when I specifically go through one of the problems. So I won't get into that one now, but we will do that a little later. All right, so that is what we're going to, those are 2 definitions so far that we'll be using for our acid-base chemistry. One other thing just to quickly mention. No, I'll mention it later. All right, we'll cut this video short. Nice little short video for you. All right, we'll see you soon.